Hello YouTube, this is the Mr. Roboto back with another Robotics 101 video. Today we're going to discuss coordinate systems. Alright, so coordinate systems. Cartesian is probably a word you've heard before. If you've had any sort of physics classes or, well, I guess really some more basic math classes in college, even back into high school, talk about Cartesian coordinate systems. But in general, Cartesian coordinate systems are what really is the foundation of what makes a robot work. Everything in robot programming is based on positioning, and that positioning is defined by coordinate systems and offsets from those coordinate systems. So, just real quick, let's define the kind of coordinate system that we're going to use in today's video. So, when I talk about a coordinate system, I'm talking about a Cartesian coordinate system, XYZ, okay? And to define the coordinate systems, industrial robots use the right-hand rule. The right-hand rule is simple. It just you make a pose like this, like you're pointing at someone. You stick your middle finger out and you put your thumb up. Okay, so X, the X direction motion is always going to be this finger. Okay, the Y direction is always going to be the middle finger, and the Z is always going to be the thumb, right? So when I was new into robot programming, I would take a Sharpie and I would write X, Y, and Z on the tips of my fingers. So when I was programming the robot, I didn't even have to think about it. I just stuck my fingers up like this. I remembered X, Y, Z. All right. So for you guys and gals newer to robot programming, that may be a good little trick for you to do. If you use Sharpie and it's stuck on your fingers for weeks and weeks, don't come complain to me. Use some common sense. All right. So, XYZ, okay? Let's take a look at this robot here. There are numerous types of coordinate systems that we use in robot programming. For the sake of not getting mixed up between terminology, between different brands of robots, I'm going to make these a little bit more of a vague description. So if you are a FANUC programmer, don't get upset if I don't use the exact terminology that FANUC uses. The same thing for KUKA and ABB and whoever else. These are just basic introductions to these topics. So the three main types of coordinate systems, I'm going to call the first one a native coordinate system. So a native coordinate system is a coordinate system that's essentially hard-coded into the robot via the kinematic equations that the engineers use to design the robot. The robot controller doesn't let you change these coordinate systems. They're not a user interface type of thing. They're sort of the base coordinate systems that can't be changed, and you don't want to change them because the other ones that are user changeable, user customizable, are referencing these native coordinate systems, and if you move those native coordinate systems, everything gets all messed up. So the two I'll start with. The first one is what sometimes is referred to as a world coordinate system. Okay, so if you look at the back of the robot, all right, again, the back is usually where the cables are at. The world coordinate system is usually center line on this axis, okay? And also center line in this direction and on the bottom of the base. So there is a theoretical coordinate system right in the middle on the bottom of this base, okay? Now, some robot manufacturers don't put it so low. Some of them will put it up higher in line with this axis. I'm talking to you, FANUC people. But for the most part, think of your world coordinate system starting in the very middle of your base and perfectly centered on this bolt pattern right here. All right. So with a world coordinate system, you take your XYZ, okay, and you point your X towards the base, all right, towards the back of the robot. So if you're standing behind the robot, right, any type of motion in this direction is a positive X motion, assuming that you're moving the robot in a straight line, okay? Any motion to the left is a positive Y motion. Any motion up is a positive Z motion, okay? So let's turn this robot and let's try and simulate this, okay? So let's say our robot is positioned like this, and we are looking at the world coordinate system. Now we're over at a different angle to the robot, so world now is here, right? So world coordinate system stays with the base of the robot. It doesn't move based on where you're standing. It always stays there. So if we do a positive X motion, which is this direction, the robot would try and move in a straight line in this direction, okay? And when I say moving in a straight line, I'm talking about this flange, all right? So when you have a articulated robot with revolute joints, which means that they rotate, anytime that you try and create a linear motion with a revolute joint robot, the joints all have to move in unison to create a linear move, all right? So positive X, this direction, all right? Now, let's say we wanted to come back towards us, positive Y direction, all right? So that would mean that the robot would try and rotate all of its joints so that you could create a positive Y motion with the flange, all right? This is kind of hard to do with one of these robots, but try and just get the understanding here. It's a Y, it's coming towards me. Let me stretch this guy out a little bit. It might help a little bit. A Y motion towards me is like this, where the wrist rotates and it allows the programmer to make a perfectly straight Y direction motion, okay? All right. Then, if we now want to go up, again, X, Y, Z, up, okay? So if we move up, this is a Z motion, perfectly straight up and down, okay? Like so. We want to move up, positive Z, move down, negative Z, okay? So, native coordinate system. First one is your coordinate system on your base, which is your world coordinate system, all right? There is another native coordinate system that is related to this coordinate system, and that coordinate resides on the flange of the robot. Okay, so on the flange of the robot, assuming that your robot is at its home position, I'm going to use my other demonstration tool for this. Most robots' home positions are somewhere similar to this, where this part of the arm is vertical, this part is horizontal. The XYZ coordinate system at the base, okay, is connected to the XYZ coordinate system on the end of the mounting flange. Okay, so these two coordinate systems are always being compared by the robot controller. All right, so if you were trying to program this robot, okay, and you were trying to calculate exactly where you needed this mounting flange to go, somewhere in space, it would be very hard for you to easily calculate what joint angle you needed to create on all these joints to get a specific position out of this flange coordinate system versus the world coordinate system. Okay, so the robot engineers know that that's not really practical to ask you to do all that math just to make simple motions. So they have simplified that interface to say what is the position of this coordinate system with respect to this coordinate system, or I should say, what is the position of this coordinate system with respect to this coordinate system, all right? So it's much easier for you to say, all right, robot, I want to go to a position of 2,000 millimeters in the X, 2,000 millimeters in the Y, and 500 millimeters in the Z. Okay, so 2,000 millimeters in the X, okay, might be somewhere out here. 2,000 millimeters in the Y might be back at some weird angle like this, okay, and then 500 millimeters in the Z might be just barely off the ground. All right, so you have a position here at your flange coordinate system that is a certain dimension in the X, Y, and the Z away from the coordinate system here at the base of the robot. The kinematic equations that drive the axes of this robot are simplified down to this XYZ relationship between these two coordinate systems. So these native coordinate systems are the bare minimum of what you need to program a robot as far as the path of the robot. Okay. The other way to program is you do have the option to program based on the angle of each individual joint. Okay, but when you look at that position in your robot controller, it's not really going to help you out that much. It's not going to do you much good because it's just going to show you a bunch of joint angles, right? Now, those joint angles are important because they make up this coordinate system reference. But if you need to be modifying that position and you just want to change it 5 millimeters in the X, if you reference your position in your robot program with joint angles, you can't change it without going in and re-teaching that position with jogging and point touch-up and things like that. And I'll get into those topics later. But if you decide to save those positions as Cartesian positions, then you could go in there and say, oh, that position's not exactly where I want it. I really would like that to be 50 millimeters higher in the Z. So you change that number in your Cartesian position, and the next time the robot executes that motion, it will be 50 millimeters higher. So these are the native coordinate systems, all right? These can't be changed. This one is always there, and it's based on the geometry of the robot arm. Okay, this one is always here. It's always the base of the robot or somewhere in close proximity to the base. Okay, so the next type of coordinate system is a coordinate system that's based on the tool that you're using. Okay, so when I say tool, I mean the piece that's bolted onto the flange. That tool that actually has the manipulation piece on it, the suction cups or the gripper, or maybe it's a weld torch, something like that. That piece that bolts on there, usually we would refer to that as an end of arm tooling, and EOAT is acronym for short. So if you ever see that EOAT, you know that that's actually not a word, EOAT. It's an acronym, stands for end of arm tooling. So let's go over to the board, and we'll go over exactly what these end of arm tooling based coordinate systems are for. All right, so end of arm tooling coordinate systems. Let's say that we have a robot here, and we are looking at the top view of the robot. Okay, and we have a tool mounting flange here. Okay, let's bolt an end of arm tool onto that flange. Okay, so I'm going to use a large end of arm tool that would be used for gripping sheet metal panels. Okay, so we bolt this tool on, and it's kind of large. It's got all these different suction cups or magnets or whatever you decide to use for your application. Okay, so we know our native coordinate systems. One of them is right here at the mounting flange. The other one is here at the base of the robot. Okay, so you could program your robot's motions to use only these two coordinate systems, and your robot would work. Okay, the path would function like it should and everything, but it wouldn't necessarily be the best process or the best programming procedure for your process. Sometimes it's good to have a coordinate system that's based on the shape of your end of arm tool. Okay, so for instance, let's say that I set up a coordinate system here, right? We're going to say this is the X, this is the Y, and then sort of coming up at an angle. That's the Z, okay? So this, think of it like this, all right, with Z here, X here, Y here, okay? So why would you possibly need to have a coordinate system anywhere different than here? Well, let's say that inside of your machine that you're loading, okay, you need to bring the corner of your sheet metal, okay, say you've got a sheet metal plate in here, that you're moving, all right. Let's say that there's some important, a corner or maybe a hole or something in your sheet metal that you have to locate into a fixture, okay? When you're programming your robot, you have the ability to rotate around your different coordinate systems, okay? So if we were looking at the flange coordinate system like this, if we wanted to rotate this sheet in this direction, okay, this way, we could rotate around the z-axis, and that sheet, that whole sheet is going to translate like this with an origin here, okay? But that doesn't really help us if we need to maintain the position of this critical geometry in the part. Maybe we want to rotate around that position, okay? So we take a coordinate system here at your flange, we create one over here that is an offset of this coordinate system, all right? So this coordinate system might have an offset dimension of, let's say, 250 millimeters in the negative y direction, right? So if it was this way, it would be positive, this way it's negative, all right? Remember the positive, negative. Positive is the way that your direction, or that your fingers are pointing. So this would have a negative y equal to 250, okay? 250, all right? It would have a positive x, okay? So that dimension would be coming from like here and maybe here, all right? So let's call this 300 millimeters, all right? So that would have a positive x equal to 300. And let's say that the z is, let's just leave it at 0. So if you were looking at this sheet from the side, it would be perfectly centered with your flange coordinate system, all right? So we'll have a z offset equal to 0 millimeters. All right. This coordinate system now allows us to come to this position and rotate around this position, all right? So the sheet would be rotating around this origin, all right? And if you think about what would happen there, the robot wrist would actually like be moving in this direction to maintain this origin, okay? Where before, the robot wrist was staying in its origin and it was moving everything else around that, all right? So this is a very powerful tool, this coordinate system, all right? And this coordinate system has a name, okay? It's called a tool center point, all right? So we're going to call this a tool center point, more commonly referred to as a TCP. Okay? So, a tool center point essentially is nothing more than an XYZ offset from your flange coordinate system. All right? So, if we go back to the example of our robot, right? Before, if there was a representation, or a relationship, I should say, of these two coordinate systems, the world coordinate system and the flange coordinate system, that was, say, 250 millimeters by 250 millimeters by 500 millimeters, okay? When you use a tool center point, you now have a third coordinate system that's being referenced. So you now, if you were to look at the position of this coordinate system in space, it's going to be the offset of this guy, right, plus the offset now of your third coordinate system. So in the, let's assume that x is in this direction, okay? Your x dimension that would show up on your teach pendant would say this number plus this number plus this number, all right? And the same thing in the y and the z direction, okay? So that is a tool center point. All right. So there's a third type of coordinate system now, and for this coordinate system, I'm going to have to get my model back out, so let's go back over to the table. Okay, so the third type of coordinate system is a work coordinate system, or a base coordinate system. Essentially, the first coordinate system, the native coordinate systems, were only in reference to the robot itself, right? The native ones. The second set of coordinate systems were based on the dimensions of your end-of-arm tooling, okay? The third is going to be based on whatever the work piece is that you're doing or interacting with, okay? So for this example, let's assume that this robot is, its process is to draw letters on this block, okay? So, and let's assume that this screwdriver on the end of the robot is what it's using to etch these letters into this block, okay? So, we have our native coordinate systems, okay? Base and the flange. We have our tool center point set up here on the end of this robot, okay? And for this demonstration, I'm going to just move the robot out, and we're going to assume that my hand is the robot, okay? This third type of coordinate system, like I said, is based on the geometry that you're working with, okay? So, let's say that you bolt this fixture to the ground and you start teaching your positions, all right? You approach your block with a positive Z offset, you move down, you make contact, and then you start etching your letter, okay? And everything's fine and dandy. This program repeats itself over and over again, and everything's just working great. But then, let's say during maintenance, or who knows what, it could be anything. It could have been caused by a crash of the robot, or whatever reason, this table moves. a little bit, right? Now, your robot program came here, it came here, and now it's trying to make this letter, but it can't, right? Because this table has moved, all right? And that's no good, because your entire robot path, you spent all that time creating this beautiful letter E, all right? That's all changed now. And if you would have used a base coordinate system or a work coordinate system, you could have eliminated the need to go in here and reteach all of these positions. All right, so that's really the main reason why this is a really important tool. Okay, again, the tool center point and the base coordinate system, they're not required to use in your process, but to be a good programmer, you need to be aware of them and use them appropriately. So this coordinate system, like I said, is based on the object that you're working with, right? So this coordinate system has an XYZ, just like the other ones, and you have a choice of where on your piece of equipment that you want to put it. Okay, you could define it in the middle, where origin in the middle, but that can be kind of hard to create that coordinate system because you have to use the tool center point to actually move it to the origin and create your X, Y, and Z. So typically when you're creating this type of coordinate system, you would have a point on your end of arm tooling or something like that, and usually you would set it to a corner. Okay, so for this demonstration, we're going to set it to the corner of the red. Okay, so then you also have the ability to set any XYZ orientation that you would like. So if it worked better for your operation, you could set this to be the Y, and you could set that to be the X. Okay. For our purposes, we're going to maintain our XYZ, and we're going to set it like this. So let's say that this is our origin, and this is our positive Y direction. This is our this is our positive X direction. This is our positive Y direction. And if that's the X positive, that's the Y positive, that automatically makes up the positive Z direction. Okay? So, if you created all of your positions here, right? Let's say that in your robot program that took you 1 position, 2 position, 3, 4, 5, you would come up, maybe back here, back down, 6, 7, and then 8. So those 8 moves. If your workstation moves a little bit, rather than reteaching all of these motions, okay, you can just reteach this one coordinate system. So you would set this as the origin. Now you would set this as your X, and you would set this as your Y. So before, your robot did a path like this, right? Your block moves. Now your robot will automatically adjust based on using a work coordinate frame. So it's a very valuable tool, all right? So just like before, well, I should say the other thing is it doesn't have to be flat either. Okay, let's say that this was at an angle. Okay, like this. You could create your coordinate system like this now, and instead of drawing an E flat on your block, it now draws it up at an angle. Okay, and you could even get crazier with it if you wanted to. You could have it rotate on a bunch of different axes, and you could draw your E in any orientation that you want. So this work coordinate system is very valuable. It's a very good tool. So I've been talking about just the X, Y, and Z, okay? But there are, within a position, there are other, there is more information that you put in, and that is the rotation of that coordinate system, all right? So for every X, Y, and Z, okay, there's a rotation around the X, okay, around the Y, and around the Z, all right? So when you're setting up your coordinate system here on your fixture, you would set an X, a Y, and a Z, okay? And then this being on a 45-degree angle would also have an angular offset, okay? So if you remember, when we talked about the end of arm tooling, tool center point, all right, the coordinate system on your tool center point here was an offset, all right? So if your tool center point's out here, that was an offset of the coordinate system at the flange, okay? Then that was translated down to the base. So really the position of the tool center point here is, let's say, 1,000 millimeters further from your world coordinate system here, okay, than your flange. So tool center point is an offset of your flange coordinate system, okay, and your work coordinate system or your base coordinate system, okay, here is an offset, direct offset of world, okay? So if you have the base of your robot in this location and you have your fixture over here, when you teach this origin, it's going to be, you're going to show 6 different values. You're going to have an X dimension offset, so that would be the dimension from here over to here, right? And then you would have a Y offset, which would be the dimension from here over to here, okay? And then you would have a Z offset, which would be your dimension from the height of this table down to this surface. So those would be your 3 main numbers. Then you would see, if it was at an angle, you would then see a rotation around, in this case, the X. If it were like this, it would be a rotation around the Y. If it was like this, it would be a rotation around the Z. All right, so that is a very quick crash course in coordinate systems, all right? So this will all start to make more sense once we get into path programming and using these coordinate systems. But for now, just know that it's XYZ and then rotations around those, which is usually represented by an ABC. So an X and an A. X is the direction, A is the rotation around the X axis. Y is the direction, and B is the rotation around Y axis. Okay, and then your C is the rotation around your Z axis. All right. So if there are any other topics that you guys would like me to cover, and any specifics maybe on this video that you would like a more in-depth explanation on, make some comments down below, and I'll try to get to that. But for today, that's all we got. Thanks so much for tuning in. Please consider hitting the subscribe button and like this video, and hit the notification bell as well if you like to see when these videos come out. I am growing the channel, so those subscriptions are super important, and I really appreciate you guys spending a couple minutes out of your day to learn about robots with me. So, with that said, the Mr. Roboto out.